All right, let's jump right into this. Welcome to today's explainer, where we're going to unpack the microscopic forces that shape the entirely macroscopic world around us. We're looking at the fundamental laws of matter, and more specifically, the hidden, totally invisible glue that holds our universe together. So if you've ever wanted to know exactly why substances behave the way they do on a physical level, well, you are definitely in the right place. To kick things off, let's ponder a real-world mystery for a second. Picture a farm. Why does the methane gas produced by a cow float effortlessly away into the atmosphere, while the water on that very same farm pools heavily at your feet, soaking into the soil? I mean, they're both relatively small molecules, right? So what exactly is the difference here? The answer, as we're about to see, lies in a completely invisible stickiness. Section 1. The secret glue of matter. Okay, so before we can really understand the different types of molecular glue, we first need to establish what actually makes a gas different from a liquid or solid. The fundamental difference between states of matter is literally just the distance between the particles. In a solid, the attractive forces between the particles absolutely dominate their kinetic energy, locking them into this fixed, ordered array. In a liquid, those forces are still strong enough to keep them close, though they can kind of slide past one another. But then, look at a gas. The attractive forces are extremely weak relative to the particle's kinetic energy, and that allows those gas molecules to spread far, far apart. Now, there is a totally critical distinction between two very similar-sounding words here. Intramolecular forces, with an A, are the strong bonds holding the atoms together inside a single molecule. Think of this as the molecule's internal skeleton. But intermolecular forces, with an E, the ones we actually care about today, are the attractive forces acting between separate molecules. This is the external sticky glue. Notice the strong solid line connecting the spheres of a molecule. That's the internal skeleton holding it together. But then there's the dashed line connecting two completely separate molecules. That dashed line represents the weak intermolecular glue. So the crucial takeaway here is that while this external attraction is significantly weaker than an internal bond, it is exactly what controls physical properties like melting points, boiling points, and viscosities. It dictates whether a substance is a solid, liquid, or gas at room temperature. Section 2. The accidental magnet. Let's start with the first and weakest level of our escalating microscopic magnets. If a molecule is completely neutral, right, with no permanent positive or negative ends, how can it ever stick to a neighbor? Well, the answer is London dispersion forces. Imagine the electrons inside a molecule are kind of like a flock of sheep in a pen. Usually, they're spread out evenly, but what if something startles them and they all randomly rush to the left side of the fence? Suddenly, that left side is incredibly crowded with negative electrons, and the right side is left completely empty and slightly positive. This creates a temporary, accidental magnet, an induced dipole that can briefly attract a neighboring molecule. So, knowing that this accidental glue relies on electrons randomly bunching up, let's think about this. Who's going to have a stronger accidental glue? A tiny, compact gas molecule with just a few electrons, or a massive, long carbon chain with a huge surface area? The rule here is super simple. More surface area equals stronger accidental glue. A long, cylindrical chain has way more surface area to physically touch and basically tangle with its neighbors, meaning its dispersion forces are significantly stronger. On the flip side, a compact, spherical molecule offers very little surface area for that kind of interaction. This is the exact reason why a cow's spherical, low-surface area methane floats away as a gas, while the high-surface area, long-chain diesel fuel sitting in your tractor tank remains a thick, heavy liquid. Section 3. The permanent magnet. Okay, we're upgrading our glue now from temporary accidental forces to molecules that are actually born with a constant built-in stickiness. Take this real-world puzzle. We have propane and acetaldehyde. Both molecules weigh exactly 44 atomic mass units, literally the same size. Yet propane boils at a freezing 231 Kelvin, which means it needs heavy, pressurized steel tanks just to keep it liquid on the farm. Meanwhile, plant-based acetaldehyde boils at 294 Kelvin, meaning it sits happily as a liquid at room temperature. If they weigh the same, why the massive difference in behavior? The answer is polarity. Unlike that random swarming of electrons we saw earlier, here the electrons are being constantly and permanently dragged toward a more greedy atom, an atom with higher electronegativity. This unequal electron sharing leaves one end of the molecule permanently partially negative, and the other end permanently partially positive. It's a permanent magnet. We call this a dipole-dipole attraction. And because these magnets literally never turn off, it requires significantly more heat energy to boil these molecules apart compared to those accidental magnets.
Section 4. The supermagnet.
We are now escalating to the absolute strongest intermolecular force. What happens when atomic greed becomes extreme? When a tiny hydrogen atom is paired with a massive electron hog, its only electron is pulled so far away that the hydrogen is basically left as a naked, highly concentrated positive proton. I mean, it glows like a beacon. This creates an incredibly strong dipole that locks onto the negative ends of neighboring molecules with immense force. Notice those dashed lines connecting them? This is called hydrogen bonding. Now, what's really interesting here is the specific requirement for this supermagnet. It doesn't happen with just any atoms. You need the VIP club of electron hogs: fluorine, oxygen, or nitrogen. If hydrogen isn't bonded to F, O, or N, you simply don't get the supermagnet. And actually, I really need to stress a crucial point here. Despite the highly confusing name hydrogen bonding, this is not a true internal chemical bond. It is strictly a sticky, external intermolecular glue. It's just an incredibly strong one. To truly grasp the power of this supermagnet, think about this. How does water travel from the deep roots of a massive oak tree all the way to leaves 100 feet in the air without any kind of mechanical pump? It's all thanks to hydrogen bonding. The water molecules hold onto each other so tightly using this supermagnet glue that as one single molecule evaporates from a leaf at the very top, it physically pulls the entire continuous chain of liquid water right up the trunk. It completely defies gravity.
Section 5. Forces shaping our world.
Let's step out of the purely microscopic realm for a second and look at how we can actually use this knowledge. This practical flowchart empowers you to look at any substance and basically deduce its properties. Step 1, are ions present? If not, we move to step 2, are polar molecules present? If the molecule is totally symmetrical and nonpolar, you know right away it only relies on those weak, accidental London dispersion forces. But if it is polar, you move to step 3. Are there hydrogen atoms directly bonded to nitrogen, oxygen, or fluorine? If yes, boom, you've identified a supermagnet, hydrogen bonding. If no, it's a standard permanent magnet, a dipole-dipole force. By following this pretty simple logic, you can predict exactly how a chemical will behave in the real world. To wrap up our explainer today, I want to leave you with this final, somewhat provocative thought. If the invisible intermolecular glue between molecules suddenly just turned off for 1 single second, what would happen to the liquid water, the plants, and these solid structures all around you? The wild reality is, without these accidental magnets, permanent magnets, and supermagnets holding independent molecules together, the macroscopic world as we know it would instantly cease to exist. It would just instantly vaporize into a chaotic, disconnected gas. And that is the true, hidden power of the invisible glue of the universe.